I thought maybe instead we could try to work on this together in the sort of the class setting. So let's talk about this situation here, and again, working through our Buckingham pi approach. So we're given that we have a sudden contraction in a pipe. The diameter changes from D1 to D2. You can see that obviously D1 is larger than D2. There's a pressure drop, delta P, which develops across the contraction and is a function of both D1 and D2. Now, up to this point, note that we have kind of talked about D in general, but there's nothing that necessarily says that D1 and D2 have to be related here, right? Like it's not some fixed ratio or something like that. Therefore, in a problem like this, we do care about both of those diameters because they can more or less be independent of each other, right? D2 could be 1 inch, could be 3 inches. D1 could be 10 inches, it could be 5 inches. We don't necessarily know what these values are, okay? And so of course, the pressure change across the contraction will very much depend on each of these diameters. Okay, and then going back, so as well as the velocity V in the larger pipe. Now, if we're already including D1 and D2, we can relate the two velocities. So in this case, if we're accounting for both dimensions, we don't necessarily have to account for both velocities. We can just deal with V1 in this case, all right? And that's what gets us around having to account for D1, D2, V1, and V2. We can just work with, as long as we have 3 of the 4, we're in pretty good shape. And then fluid density, obviously, which has something to do with the inertial forces, and then viscosity, which has to do with drag or friction of the forces here. So what we're being asked to find is use D1, V, and mu as repeating variables to develop a pi term relationship. So in other words, pi 1 is equal to phi times, or phi as a function of pi 2, 3, 4, however many we need. So we'll go through the evaluation of that here in just a second. Why would it be incorrect to conclude that the velocity in the smaller pipe should be an additional variable? Okay, well, I sort of just explained that. So I guess I got a little ahead of myself. My apologies there. But essentially, the point is simply that because we can relate the two diameters, we should be able to relate the two velocities, right? And so when it comes to the pi term approach here, we don't necessarily need to account for both velocities. All right, so let's get started then on this process of identifying what our dimensions look like. So we've basically been told that we care about delta P, the pressure drop, and it is some function of D1, D2, the velocity, oh goodness sakes, V1, rho, and mu, right? We only have one fluid here, so we have one rho and one mu, one viscosity to worry about. So there are 1, 2, 3, 4, 5, 6 variables. So K equals 6 variables. And for each of them, let's take a look here. D1 and D2, of course, are going to be in dimensions of length. Our velocity V1, of course, is in dimensions of length per time. And then mu, our viscosity, density. Let's see, are we going to work in, why don't we work in force? In which case, let me have it here. Give me just a second. Mu is, I think we wrote it the other day at the end of class on Thursday. Just find that value real quick. There it is. Okay, F, force, length to the -4, time to the minus, time, let's see. Yeah, I think it's just time. Okay. And then mu, our viscosity, move that guy out of the way. Viscosity is in terms of, oh, sorry, this should have been squared. Sorry about that. So that density there should have a squared time component or dimension. Mu is f L to the minus 2 t to the 1, and put this guy down here maybe. And then what's our last one? Oh, delta P. In this case, it's just pressure terms, right? We're not, before we looked at pressure change per length. So our pressure term here is just force length to the minus 2, okay? So we have 6 variables, and we have 1, 2, 3 dimensions. I chose FLT. We could have worked in MLT just as easily, but all 3 of them are represented here. And so R equals 3, which means that the number of pi terms is equal to 6 minus 3 equals 3, okay? So we will have some pi 1 is equal to some function of pi 2 comma pi 3, all right? And we've been told that the repeating variables are D1, V, or V1 rather, in this case, and mu. All right. Now, in all of those, across those, we do have force, length, and time represented. So we should be in good shape. Like that seems like good advice that we are able to follow that. Okay. So, so those are repeating. So let's start with our pi 1 term. So pi 1, we can start with, generally on that left-hand side, remember, we're trying to predict delta P as a function of these other things. So we typically like to put that thing that we're looking for on the left-hand side. And so pi 1 would be some delta P, and then our repeating terms, D1 to the A power, V1 to the B power. Sorry, that's not supposed to be a cross. It's not a volume, it is velocity here. V1 to the B power and mu to the C power, right? And of course, we need to figure out what A, B, and C are so that F to the 0, L to the 0, T to the 0 is realized, right? Is mathematically works out. So what is delta P? We said it's force length to the minus 2, and then the dimensions of D1 are just length. Raise that to the A power. The dimensions of velocity 1 are length time to the minus 1. We raise that to the B power, and then mu, we have force length to the minus 2 times time, and that's all raised to the C power, and again is equal to F naught, or F to the 0, L to the 0, T to the 0. So how do we get these subs or superscripts to work out, these powers? So for force, we end up with, we have 1 here, and then we have nothing in A, nothing in B, and then we have a plus C is equal to 0. And so that tells us that C is equal to a minus 1, right? Okay, well, from one equation, we got one unknown so far. Let's work through the other 2. For L, the length dimension, now we're going to end up with, we have a minus 2 here. So minus 2, we have a plus A, right? We have plus B, and then we have a minus 2C equals 0. Now, we know what C is. We don't know what A or B are, so we can't quite resolve this yet. So let's go to time. For the time dimension, we end up with nothing here, nothing here. We have a minus B there. We have time is raised to the C power, so add a plus C, and then, of course, equals 0. Now, what this means is that B is also equal to a minus 1. Right? So if C is a minus 1, into this equation to satisfy this, we need to have B as minus 1 because it's got a negative in front of it. So those 2 work out, and this should allow us to solve for A being equal to 1, right? So if we plug into this, right here, -1 and a -1, we would get, with this -2 out front, we'd end up with A being equal to 1. So pi 1 is equal to, basically delta P is always in the numerator, whatever that non-repeating parameter is in the numerator. And then it turns out we also have this thing raised to the A, so D1 is in the numerator. And then we divide by, and we've got two things in the denominator, right? The whatever B is the power for it, so in this case that's V1. And then we have C as well, so that's, this was mu. Okay, so there's our row 1 dimensionless number that would go into this equation right here. Okay, so now we need to solve for pi 2 and pi 3, and we can do that on the next slide. I think maybe to save us a little bit of time, I'm going to lay out what pi 2 looks like, but I'm not going to go through the algebra of the system of equations. And I'll just note what the pi 2 value is, just to save us a little bit of time. You can go back and check with your own work to see if that works out the right way or not. And certainly if you have questions, feel free to ask, send me an email and ask. Okay, so pi 2.
I have a quick question.
Sure.
Like, how did you decide that D1, V1, and mu were the pi 1 term?
Well, those are the repeating variables. So they always have to be included in all three pi terms. They will show up. And Amara, that was defined right here. Use these as the repeating variables. So
Gotcha.
One of the things that I think is super confusing myself is to try to identify the repeating variables. So those are always going to be given to you. And so, in this case, what did we have? I think so. In this case, we had delta P, D1, D2, V1, rho, and mu. We know that D1, V1, mu are the repeating variables. So each of our pi terms then will have to include P1 or delta P is non-repeating, D2 is non-repeating, and rho is non-repeating.
Okay. Yeah, that makes sense. Thanks.
Sure, no problem. Okay, so now pi 2, let's use the second one of these, and it's just easiest to work in order. So the way I wrote these out, now let's put D2 as our non-repeating variable. So this is going to be equal to D2, and then we need to include the three repeating variables, and each one of these will have that A, B, C exponent. So now multiplied by D1 to the A power, V1 to the B power, and mu to the C power. And obviously our goal again is to get F to the 0, L to the 0, T to the 0. And what this comes out to in dimensions is L times L to the A times, let's see, L T to the -1 raised to the B power. And what do we have? This is mu is in force, lengths per length squared, time, raise all that to the C power is equal to, again, F to the 0, L to the 0, T to the 0. And what you should find is that A comes out to be -1, B comes out to be 0, and C comes out to be 0. So I'm skipping the part of creating those three equations and three unknowns. But what this boils down to then is that pi 2 comes out to be D2 over D1. And of course, both of those are length, and so dimensions of length. So that 2 is a dimensionless number, right? We can sort of identify that pretty easily without having to do any math to sort of figure that out. Okay, let me just change up my color here to work on pi 3. Let me go through about the same level of detail here for pi 3. So now we're going to use our repeating variables again, but the other one that hasn't repeated is rho. So we will now include rho and then D1 raised to the A power, V1 raised to the B power, and mu raised to the C power. And of course, we want this to be F to the 0, L to the 0, T to the 0. And so now our dimensional analysis looks like this. We have force length to the minus 4t to the t squared for rho, and then we have length to the a power. The dimensions of velocity are length times the minus 1 raised to the b power, and then mu is force per length squared times time, all that raised to the c power. Again, we need to figure out a, b, and c so that it is satisfied that we have f to the 0, L to the 0, t to the 0 power. I'll skip the step of making those three equations and three unknowns, and ultimately you should find that a is equal to 1, b is also equal to 1, and c is equal to a minus 1. So pi 2, or 3, pardon me, is now we're going to have rho, our non-repeating variable, in the numerator. And then what happens with our others? So a to the 1 means that we have d1 in the numerator. And then b is also to the first power, so we end up with v1 as well in the numerator. And then in the denominator, because we ended up with c being a minus 1, we would get mu. Okay? So there's the third pi term. And now what I'm going to do on the next slide is just put all of these together in one, going back to that master equation. Pi 1 is equal to phi, pi 2 comma pi 3. Let's just put those together in one equation and see what it looks like. Okay. So that ultimately looks like this. You end up with pi 1 is equal to phi, some function of pi 2 comma pi 3. And when we substitute in these values, we found delta P, the pressure, times D, let me make sure I get the right D on that one. Should be D1. I didn't have the 1 indicated in my notes. Divided by V1 times mu is equal to phi of, and then we write these out, D2 over D1, comma, rho D1 V1 over mu. So what this means is that if you were an experimentalist and you wanted to figure out the relationship among these groupings, you would conduct an experiment at maybe different pressures, or you would read the pressures for different diameters, velocities, or mu's, what have you, and you would come up with this dimensionless grouping on the left-hand side and quantify that. And then you would look at how this changes with different D's, the ratio of D2 to D1, to see if there's a relationship between the grouping on the left and that first grouping on the right. And then you would do the same thing again for the dimensionless grouping on the left with the second dimensionless grouping on the right-hand side. And sometimes there is no relationship at all. Sometimes there is one. And so we'll talk about that in a minute in an example I have queued up here. But the dimensional analysis at least takes us to this point of having put all of these together to explore the right relationships that might exist. Okay?
I have just one question.
Sure.
Is there any way to tell which ones you picked as the repeating variables?
Yeah, I mean, so the recommendation is generally like the simplest ones, which is a little bit hard to identify. And so, for example, I mean, let's just go back to this one real quick. We had, we needed to have, in our repeating variables, we need to have all three: force, length, and time represented. We ended up with we were told mu, D1, and V. It probably could have been mu, D2, and V1, or even V2 instead of V1. But for whatever reason, like, this is where I've kind of struggled with the Buckingham pi approach. If you chose a different approach, like you used rho instead of mu, ultimately I think you would find out, you would work through it and find out it didn't work. So you'd kind of get to a dead end and then come back and have to start over and say, okay, I can't use that as a repeating variable. Let's use this instead. So what I'm trying to indicate to you is that in the exam or anywhere else that you see a problem like this, you should get this kind of a statement to guide you as to which should be the repeating variables. Does that help a bit, Magnus?
Yeah, thank you.
You bet. Okay. So we've talked a little bit about some particular dimensionless groups, and some of these, of course, looked kind of random the way in the problems we've worked, maybe with the exception of the Mach number, right? We were told that Mach actually means something when we worked through one of the examples yesterday in recitation. These common dimensionless groups are really pi terms from particular problems, but they are so common that we give them these sort of special names, typically after whoever identified them back in the day, and can use them over and over. And rather than saying, oh, this pi group that has this, this, and this in it, you say, no, the Reynolds number, the Mach number, the Weber number. These are identified now as sort of summarizing phenomena that we may care about in other parts of fluid mechanics. So I'm just going to walk you through a handful of these. And I just want to point out before we get started that in a lot of cases, I'm going to write the equation, and then next to that, I'm going to interpret it as like inertial energy divided by kinetic energy or something like that. These are not in energy terms. They are just representing those energies. So for example, if we had velocity included, we might call that kinetic energy, right? But it's not actually in energy units, just the representation of that energy in some way is included here. So just as an FYI, don't expect these to come out to energy units in the numerator and denominator, but they are dimensionless numbers. The Reynolds number is one of these that's quite important. We use it to identify when flows are turbulent versus laminar, and we come up with thresholds for that, but it's basically the density of the fluid multiplied by its velocity times some characteristic length. So that characteristic length, for example, in a pipe would be like the diameter of that pipe, and then divided by mu, okay, the dynamic viscosity. Now, ultimately, this can be interpreted as the ratio of inertial forces or inertial force to viscous force. Right? Again, these are not in force units, or energy units or whatever. They are dimensionless, but we can convert these to some sort of energy or force representation if we wanted. These are the Reynolds number is typically used in lots of different types of fluid dynamic problems because we care about whether we have laminar or turbulent flow. We may treat the use of these differently. Or the way in which we deal with a particular flow differently depending on whether it's turbulent or laminar. Sorry, my phone is buzzing. Let me turn that off. Okay, the Fruit number is another number that we, dimensionless grouping that we care about. I do this double because that's kind of typically the way we write it, but it's used because we're sort of indicating that what we'd like to do is make this bold, but we don't usually, write in bold. So we do this double backbone sort of to indicate it's an F that we otherwise want it to be bold. That's the ratio of velocity divided by the square root of the acceleration due to gravity times, again, some characteristic length. That could be the depth of flow. In a pipe, it could be the diameter or something like that. This is the inertial force ratio to gravitational force. Okay. Flow of the free surface is generally the way in which the Fruit number is used, and we use it to think about how energy will change if we go through some flow depth change, for example. That's something you'll get into in hydraulics. Just a little bit of a teaser there. The Euler number, EU, is equal to P pressure divided by rho V squared. So here we're looking at the pressure force ratio to the inertial force. And this we typically use in problems in which pressure or pressure differences are of interest with flowing fluids. With the short time left in this class, of course, we're not going to put all of these to use. I'm just providing them as sort of an overview as common pi terms that come out of this Buckingham pi approach. The Chaucy number is Ca, and it is equal to the ratio of rho v squared over E sub v, where E sub v is our bulk modulus of elasticity. And in words, that is the ratio of the inertial force to compressibility force. So more commonly used with gases than liquids necessarily. Flows in which the compressibility of fluid is important. And then the Mach number we talked about a little bit yesterday, MA, it's equal to a velocity divided by the speed of sound. And in this case, we interpret that as, again, inertial force relative to, in this case, a compressibility force. And that comes back mostly to gases. So slightly different with this representation using the speed of sound in the denominator rather than the bulk modulus of elasticity. So flows in which the compressibility of a fluid is important. So this is the same for both, or the use of both of these. But in general, that Mach number is something we use for like jet airplanes and things like that, right? When you're going faster than the speed of sound or less than the speed of sound, we can put that in a Mach number and recognize what that's equivalent to. Okay, just I think these are the last two. The Struwell number is represented as ST. It's equal to omega times L over V, where these are now, remember, go back to the rotating sprinkler heads. Omega here is the velocity of that sprinkler head, and V would be like that whole sprinkler moving somehow, right? I don't know if you've seen the sprinklers that they look like a little tiny tractor, and as they whip around, they're also slowly sort of rolling across your lawn when you use those. That would be like these two velocities here. One is that local velocity, and the other one is more of a convective velocity. And so this is a local inertial force normalized to a convective inertial force. Okay, so unsteady flow with a characteristic frequency oscillation, or something like I was thinking when I was writing out my notes, I was thinking of from the Austin Power movies. Isn't there a scene where Mini-Me comes out and he's in space and he's sort of spinning, but he's also moving at the same time? So if that chair is spinning, that's sort of the local inertial force, and the fact that the chair is also moving through space is the convective inertial force. That would be one way to think about it. If you want to stick with the Mini-Me sort of view, that's totally okay. We could call him Mini Struwell, and you could keep that in your memory bank. All right, the Weber number, WE, is rho v squared L, some characteristic length, divided by sigma. Now we have surface tension included. So this is the ratio of an inertial force divided by surface tension force. Okay, and the inertial force here, clearly something is moving. We didn't really talk about things that are moving with respect to surface tension, but this could matter in, say, chemical engineering context when you're having different fluids mixing or something like that, or having to flow and then mix in some way. All right, let's set those aside now and think a bit about what we do with these dimensionless numbers after we bring them together. So whether we've identified our pi terms in the Buckingham pi approach, or whether we're using them, some of these common dimensionless groups that we've just defined on the past 3 or 4 slides, we need to think about how we put them to use. All right, so let me do that with a little bit of an example here. So one of the most important uses of dimensional analysis is aiding in the efficient, I misspelled that, handling, interpretation, and correlation of data. Oh, handling, that should be a G. Okay, so on the right-hand side, what we see here is the Reynolds number on the x-axis for a model or a full-scale mock-up. We're not really given that information, but if we had the information, we knew what fluid it was, we knew the velocity it was going, and we knew the diameter it was flowing in, and of course, whatever fluid it is, it has some viscosity. We can calculate the Reynolds number, how it changes with velocity, and then relate that to this other dimensionless grouping, which is diameter times the delta PL, that change in pressure with length, divided by rho v squared, right? So we could measure all these things, and you can see that there's some kind of a relationship that comes out of that. That for the specific dimensions that we have here, and the range of velocities that we have, the type of fluid we have, this is how these two things are related to each other. And ultimately, that should allow us to perhaps predict what delta PL will be given a D, a V, and a rho, right? You could imagine that for a Reynolds number of 20,000, right, you can pick out a value over here, 0.013 perhaps, solve that for delta P, and you can figure out what delta P is. All right, so this starts to inform or give us the ability to predict exactly what's going to happen. For example, the experimental functional relationship between the Reynolds number and pressure can be found using experimental data for the pressure drop problem that we've discussed last Thursday a fair bit. Okay? All right, so what I want to do in the next two sets of slides is we'll go through an example. It was again supposed to be an exercise that you guys work through, but in the interest of time, I think we'll work through it together. We're going to do what we've done before, identify pi groups and so forth, and come up with this equation, pi 1 is equal to phi, pi 2, pi 3, whatever. And then what we're going to do is say, okay, now I've got some experimental data. We've already identified the pi groups. How do they relate to each other? Okay, so this is kind of a two-step process. So let's start the first step, because you guys can probably already do this fairly well by now. Sorry, I forgot about this. Oh, sorry, you may have had this one showing on your slides. This is just if we log transform the two axes, we end up with a straight line, right? That curvilinear line told us that it was a log normal relationship. This one confirms that because it's a straight line in log space. So it would be a power law relationship between the two. And if we can fit that line has an equation to it. This is your X and this is your Y that you could basically put together. And we'll talk about that in the step beyond this exercise. Okay, so first of all, in this exercise, we're asked, as shown below, you have a rectangular barge. It floats in a stable configuration, provided the distance between the center of gravity and the object, or the boat and the load, the center of gravity of the object, the boat and the load, and the center of buoyancy, C, is less than a certain amount, H. If the distance is greater than H, the boat will tip over. So we want to assume that H is a function of the boat's width, B, length, L, and draft H, right? So draft is how deep it is in the water here as it's floating. And B is the width. So we're looking at this from the side. And then here's our H, the difference between the center of gravity and the center of buoyancy, right? Okay, so how are we going to put all this together? The one thing I'll note is that B is repeating. So that's our repeating variable here, just to provide that as a given. Now we've got 1, 2, 3, 4. So H is equal to some function of B, L, and H. And of course, B is our repeater, right? So we've got 1, 2, 3, 4. K equals 4 parameters. Now let's think about the dimensions of these. B, of course, is going to be in length. L is also going to be in dimensions of length. H is going to be in dimensions of length. And big H, capital H, is also in dimensions of length. So we have K equals 4 parameters, R equals 1 dimension. So we're going to have 3 pi groups. Okay? But they're super easy to figure out. So despite that sounding a bit intimidating, these are actually quite simple because all we have are lengths. So we can have an H over a B, an L over a B, whatever. So let's reason our way through that. Remember, little b is our repeating variable here. So pi 1 is equal to, we said that, I'm just going to go back here real quick. We said B was repeating. First, we need to start with H as the thing we care about. So pi 1 is equal to H, which is not repeating, times B, which is repeating. And of course, so for dimensions of length, we get 1 plus A, and that's got to equal 0, right? Because this has to equal L raised to the 0 power. So A basically then is going to be equal to a -1. So what that means then is that pi 1 is equal to capital H over B. Okay, does that make sense? So these are way simpler than the ones we've talked about to date. Pi 2 is going to be similarly simple. Now instead of capital H, we're going to use little h. That was another one that was not repeating. So b to the a power. We basically are going to come up with, going through the same process, we will get that pi 2 is equal to little h over b. And pi 3 now is equal to L times b to the a power. And I'm just skipping the step of creating this equation here for us. But pi 3 comes out to be L over b. L over b. Okay? So now our equation looks like this, the master equation from the previous slide. We basically have that H over B, this ratio, is equal to some function of little h over B and or L over B. Okay? Okay, so keep that in mind for just a moment as we now switch gears and say, okay, now let's say that we've got this, some data, all right? The results of some experiments with a model barge with a width of 1 meter. So B is equal to 1 meter, right? We didn't change B. We had one 1 meter width barge that we could do some experiments with. And we modified L 2 different ways. We have 2 meters and 4 meters for L. We modified little h from 0.1 to 0.35. And we modified big H, came out, it's 0.833, 0.417, and 0.238. So we put these combinations of these together. And when we calculate, so that's when we calculate L over B, H over B, and big H over B. Remember, we just said a second ago, I want to rewrite it just so we keep it in mind. We said big H over B is equal to some function of little h over B, comma, L over B, right? So it looks like that. So we need to compute big H over B. So there's our pi 1 term, little h over B given there, and then our L over B, which is given there. So we've calculated these. It turns out because B is equal to 1 meter, these are all really simple to equate, right? We've just basically taken all these terms, divided each of them by 1, and we end up with the same values essentially over here. Now, the key to this, though, is in a spreadsheet or something like that, we can now take these calculations and look at big H over B as a function of little h over B, big H over B as a function of L over B, and we could relate these two if we wanted to as well. So remember, this is a pi 1 term, this is pi 2, and this is pi 3. And I wasn't able to find the superscript for my Excel on the next slide for the headers, but this is what pi 2 versus pi 3 looks like. Maybe this was a little too much. We probably don't have to show this, but you can see that there's no relationship. Now, there wasn't predicted to be a relationship. These are both things on the right-hand side of the equation. So, not necessarily expected, but confirmed our expectation. Now, the second one, though, is now pi 1 versus pi 3. Oh, now here we also don't see any relationship at all. So that means that P1 as a function, let me go back and rewrite it here. Pi 1 equal to phi of pi 2 comma pi 3. When we look at pi 1 versus pi 3, not much going on there at all, right? Like there's not a solid relationship there. However, when we relate pi 1 to pi 2, now you can see something has developed, right? We could try to fit a line through this, but it turns out that if we use a log normal plot or a power law plot here, we end up nailing these, right? So r squared equal to 1. And what this equation basically comes out to is y, h over b, big H over b, is equal to 0.0833 times, in this case, little h over b to the minus 1 power. Or we could have just written that as little b over L, essentially. Okay? So that's the way in which, so it turns out that there was no relationship between pi 1 and pi 3. That's okay. I mean, the Buckingham pi theorem does not necessarily tell us that every one of these are going to be related to each other, because part of that function could be, you don't really have to worry about one of these terms, but you do have to worry about the other one. So in this case, we had to worry about one of them and not the other, and clearly this comes out with a really solid relationship, again, for relating these two. Now, real quick, just as an aside, I did plot all of this in Excel. It was fairly straightforward to go from this step to when I was at this step, I could right click on the data points, one of the data points. And when I did, I got options for fitting a curve to the data. And then you can choose what type of curve you want to make that. Is it linear? Is it exponential? Is it logarithmic? Whatever it is, Excel will figure it out. And then you can also choose to show the equation for that line and the r squared. So in this case, I just selected all three of those options, and boom, I get a really nice fit that helps me solve this. Now, I could have found some other way of trying to figure out how all these things are related to each other, but Excel is a powerful tool for being able to do some of these things. Okay. All right, so the last topic here is modeling and similitude. The idea that we still need to kind of figure out how is a model going to represent the full-scale processes that are occurring. And again, we want to focus on these dimensionless relationships. How will they guide us? So in engineering, we're often interested in predicting the system response to some proposed change. But it's often expensive and physically impossible to test changes on the real system. So we experiment essentially using scale models, right? We've talked a little bit about scales and so forth. And I want to show you 3 examples real quick. So I'm just going to pop out of this and bring up, yep. And then I just need to bring up oh good, some thunder outside. Well, let's see. Let's see if I can do this with my left hand. All right, so we can get rid of that. It looks like we only have 15 minutes of class left. Somewhere in here I had, popped up over here. So moving this over here. All right, so we're looking at, a town of some kind of a layout. Maybe it's a campus. Obviously, these are kind of scaled buildings. And then we've got this other sort of scale in this downwind. And the idea here is if we are putting out some sort of fluid from one of these locations, we could try to predict where that fluid is going to go, who will be in that plume downwind. Right, so that's a simple way that we could use to try to predict perhaps concentrations or exposure to some of these releases. All right, that was 7.2. Let me pull up 7.3. Okay, let's make this one big enough to see. This is hatchery pond. So this is where we would rear fish for trying to introduce them back into the real world. This might be the model that's developed, right? So if we want to think about how long it takes for, creating inlets, how much our flow is going to be, we could simulate these and look at flows. Like, for example, the fish that are being reared maybe can't be in an environment with a velocity of a particular threshold, something like that. Then we could work on this design in a model way before we build the prototype. Model walkway and exit here for our stock or our hatchery and so forth. All right, finally, the last one I want to show you is 7.6. So let me pull that one up. Where did my cursor go? There it is. Okay, now in this case, we're looking at, like a bridge crossing with a bunch of material debris that's going to get caught on the footers, right? So, this is some simulation of a scaled representation of the real world, and all this debris is at some scale as well, right? So how big are the forces maybe that are going to impact the bridge and its structure? Will it potentially fail and so forth? These are the kinds of things that we could assess potentially in the model domain so that we don't risk an expensive investment in the real world. All right, let's go back to our... And by the way, this, of course, is all too familiar to anybody who's lived around Boulder or Fort Collins in the past, say, 7-ish years or so, 6 years with the big floods that we had in 2013. There were times here on the Poudre. It took a while, but the city eventually shut down a couple of the bridges that crossed the Poudre, which sort of isolated North Fort Collins from the rest of town. And this is what they were concerned about. Not as much the overtopping as collecting a bunch of debris that could cause the bridge to fail in some way catastrophically. Okay, so let's go on here. So how can can you design a scaled model that accurately predicts the system behavior? Well, ultimately, what we're trying to use are these scaled models, and we can get my pen going again. The answer is to use dimensional analysis principles, where ultimately we are going to be looking at specific relationship here, where we would say that pi 1 is, of course, equal to pi or some phi of pi 2, pi 3, etc., all the way to some pi n, right, for a given system. Right, so the relationship requires only general knowledge of important system variables. The relationship should apply to any system governed by the same variables, but the smaller model we expect that we're going to create some smaller model with similar behavior. So how do we dictate what that similar behavior is going to be so that we can have the power of prediction? All right, so what we want to do is come up with a dimensionless relationship for the model to be similar to what is given in the real system. So we would say perhaps pi1m, where m designates the model, is equal to some phi of pi2m, pi3m, etc., all the way to pi nm, right? So we would have these set of pi terms, and they would go out as far as they need to based on k minus r. But we expect that the model is somehow going to be predictive of the real system. And so what we mean by that then is that, one, similarity will require that all of the corresponding pi terms must be equated between the model and the system. We might call the system the prototype, right? The sort of real world system. Two, we also expect that the prediction equation must have the same function for the model and the prototype. So in other words, whatever relationship we come up with the model has to end up being valid for the real system. How do we know that's the case? We may not until we really build out the prototype and test it. At this point, we probably have an awful lot of opportunity to look back at examples that others have produced to be able to determine whether we're going to be fruitful or not in that approach. But there's still a lot of value to doing this. So what I'm going to do is wrap up these concepts of similarity. Complete similarity is a function of three types of similarity. The first being geometric. We'll go through those, but it looks like I won't have time for the last example here, which is kind of working through a couple of these bigger Buckingham pi approaches. Don't worry about that. I won't hold you accountable for those last two examples that are included here, just these concepts that we'll finish up right here. So geometric similarity is when a model must be a scaled version of the system, including the finest features of the system, such as surface roughness. It's weird. Surface roughness. That may significantly influence flow. This is achieved by mostly accounting for important lengths, right? The length dimension of the model and the real world system, 1/10, 1/20, whatever it's going to be. Then there are two other types of similarity. One of them is something we call dynamic similarity, and the other one is kinematic similarity. So let's define those. Curious. All right, dynamic similarity requires that the ratio of forces in the model and the system be the same. So in other words, dynamic similarity is something we're often going for when we think about the ratio of these different forces, like we talked about with those dimensionless groupings earlier. This is achieved by equating important dimensionless groups. Oh, I guess I have groups in there already. So in other words, this is thinking about the Reynolds number, the Froude number, the Mach number, those kinds of dimensionless groups that are already defined. Kinematic similarity is when we have corresponding velocity ratios and so this would be like a V model to V prototype, right, in a particular part of the model, a particular part of the prototype, and acceleration ratios A sub m, let's say an acceleration in the modeled domain divided by an acceleration in the prototype domain are constant in the flow field. Okay, so the values don't have to be identical. You don't have to have the same acceleration as in the model as you do in the prototype. You just have to have the ratio of them be the same for, let's say, different parts of the system. Okay, finally then, I just want to provide one little note of caution here on this concept, which is that given geometric and what do we call it? And dynamic similarity, the streamline patterns will be the same for both systems, that is the model and the prototype, implying that you have kinematic similarity. Okay, so that's important to an important aspect of this. Okay, we will end there. Let me just, the last thing I'll do is bring up the, I'll fast forward here to the participation question for the day. Just make sure everybody got that. It's a pretty small amount of writing, so move ahead here. Okay, for flow in a pipe, the Reynolds number is defined as V rho D over mu, where V is the velocity, rho is density, mu is viscosity, and D is diameter. Expressed this way, the Reynolds number can be interpreted as one of these four options. So go ahead and get started with putting your vote in. We did cover this a couple slides ago, so you're welcome to go look at that if you'd like. It was when we were assessing the common dimensionless groupings, I think we called it, something like that. Okay, we're at 66 and 35 seconds. How are we doing on? Okay, we've got 78 folks online, so hopefully we'll get a little closer to 75-ish. We'll go all the way to 60 seconds here. Nine more seconds, try to get your voice heard. All right, 78, that's good. And we'll end there. Okay. Well, let's take a look. All right. Looks like the most popular vote here, and I appreciate that E was not one that anybody chose, but the most popular was B, the ratio of inertial to viscous forces, which is indeed correct. This is our inertia because we have V involved, and then, of course, viscosity is in our denominator there. It's in the name of the item that's there. So with that, I appreciate having seen you all today. Glad we made it to week 15. We'll have one more class on Thursday, so I look forward to seeing you then. But otherwise, have a great week. And and just the last thing, Emma and I will have our normal office hours tomorrow, so you're welcome to come by and see us. And we'll be happy to chat with you then if you have any questions about the homework. Otherwise, take care and have a good evening.
Thank you. Thank you.
Mind going back to the kinematic similarity slide really quick?
Let's see.
I think there's a second to last.
Kinematic. Yep. Did I just turn off my share? Sorry. Let me close this real quick and reshare. Okay, there it is.
Thanks.
You bet. No problem. Any other questions?
Will there be posted any practice final stuff?
Yeah, I'll post that. I think I committed to doing that by Thursday. I can't remember if I said tomorrow or Thursday, but yeah, I'll get that posted. And then the idea is that there won't necessarily be solutions to those, but that's what in part the extra office hours on Friday can be. If you want to take a shot at working through them, and we can talk through them on Friday.
Okay. Yeah, so you won't have any chance to post them before that. It's just because I have 4 finals coming up and I have to try to distribute my efforts.
Yeah, understandable. I've collected some of that info, but I probably am not going to have the time to put it together until tomorrow night, or tomorrow at least. So I could probably get it posted tomorrow night, but that's probably the earliest I'm going to be able to do it.
Okay. Well, thank you anyway.
All right. Yep, no problem.
Yeah.
I just had a really quick question about determining which variables are repeated, because like in part 3 of homework 12, it doesn't, like, part 2 kind of guides us to like see which ones are repeated. Part 3 doesn't really do that, so I was wondering if there's like a method.
Oh shoot, yeah, it's a little bit gut sense. Yeah, sorry, I didn't realize I didn't have those defined for you in part 3. Let me see, I just grabbed my homework, but I think I've got it completely out of order. I don't know what I did with part 3. Okay, here we go. So sewage filtration plants. Okay, so you've got W, mu, volume, and G, the velocity gradient. Okay, so you definitely want to include, so W is the thing you don't want to have repeating, right? It's the thing you're looking for functions of. And then, sorry, did I miss it?
I just said okay.
And there's only one pi group, so that you're done at that point. If you pick W as the non-repeating, then.
Okay, sweet. So we have like W is a function of mu, volume, and G.
Yeah, that should be right.
Okay, sweet. Thank you.
You bet. Yeah, I guess repeating once isn't really repeating, is it? Yeah. Hi, Sophie.
Hi, I just had a quick question on the first extra credit.
Okay.
I was just wondering if you'd finished grading those, because I was looking at them.
No, I haven't. I'm probably halfway through. It turns out it takes a while to read everybody. So.
Okay, yeah, no worries.
I'm sorry.
I'll probably be last, but
Sophie, I probably should have started that one at the bottom of the alphabet, but unfortunately it was a W. We must have, I think there are like 20 people whose last name starts with an A in this class.
Oh no, really?
So it takes me a long time just to get out of the A's. But by the time I'm in F's, I feel pretty good. So, yeah, sorry about that, Sophie. I'm going to try to get those done soon because I don't want them hanging about. But at the same time, I want to get you guys the information. So
for sure. Thank you.
You bet.
And then I had a question about number 5 and the extra credit, but I can also come back for your office hours tomorrow if you'd rather me do that.
Yeah, I need to jump to another meeting right now. So if you don't mind, that would be awesome. Or you can send me an email if you want. I'm happy to respond.
Okay. That sounds good. Thank you.
Okay, you bet. Take care.
Bye.
Mohammed, did you have any questions?